We good?
All right. Good afternoon, everyone. Hope you had a nice lunch. We're ready to get the afternoon session started. We have two plenary talks, which should be very exciting. The first talk will be Nicolas and Ross from Google's network engineering team. They're based out of the Asia-Pacific region. They'll be talking about some topology-aware monitoring system that they've been building at Google.
Thank you. Good afternoon. So I'm Nicolas Guilbaud, and with me is Ross Cartlidge. We are both from the senior office of Google in Australia, although only one of us is Australian. But you guess which one. So we are here to talk about actually a project that we started a couple of years ago. And we started this project out of frustration of doing like manual troubleshooting. So instead of spending like minutes and hours of troubleshooting to find actually the root cause of packet loss in the network, we thought actually there must be a better way. So we thought we want the machines actually to do the heavy lifting. We want actually machines to be able to help us out and find the network elements which are faulty in the network and not humans. So typically, network operators use white box monitoring to monitor the network. And white box monitoring is primarily basically asking network devices about their health. So what's your CPU usage, what's your memory usage, what's your interface load, and so forth. Unfortunately, too many times, the monitoring is clear, and yet network elements are discarding packets or corrupting packets. So sometimes actually the monitoring doesn't provide us the right answer. They tell us that the egress line card is actually corrupting packet, but actually the corruption happens on the ingress, confusing the network operators. Or even actually the packet is lost. So imagine a syslog message with a critical message such as RIP-FIB synchronization issue, and that message can be dropped, and suddenly the network is compromised and the operators are not aware of it. So to augment the white box monitoring, operators like Google basically deploy black box monitoring on top of it. And black box monitoring is basically a bunch of sender and that was the time. Sender and receivers that basically are scattered around the network and send keep alive packets between each other. And we monitor basically the result of those keep alive, and we report metrics such as packet loss, latency, and jitter. This is great, but it's got actually two major issues. Only the best paths between those sender and receivers is monitored really. So if something happens in the middle of the gray cloud area instead of the blue dots, nobody knows. And also, actually, it's kind of hard to isolate the issue. We know there's a problem, but actually, we know there's a problem between the end-to-end packets, but we don't know where the problem is. All right, so that's not good enough. Actually, we wanted more. We network operators wanted more. We wanted actually complete coverage. We didn't want to test only the best path. We wanted to test every single path. We wanted to test every single device and link in the network, not only the best path. And we wanted actually the system to tell us where is the problem coming from, not that we have a problem. I mean, knowing that we have a problem is a good thing, but telling us exactly what the problem is much better. And we want to be able to monitor or test traffic on devices which are not yet in production. Typically, we don't want to use your search queries and YouTube videos to discover that we have a problem in our network. We want to be able to actually bring a brand new box and test it before putting it live in the network. So how do we actually cover every single element? We could be running something like IPSLA. We could be running something on the CPU of the network elements and pinging all the adjacencies of the neighbors. But as we discovered, the traffic from the CPU is not switched like the production traffic. It doesn't go for the switching fabric. Actually, I've got a good example in a network, not Google. It will never happen at Google, and not me. Once in a while. So there was this team that actually brought up a new box in the network. So they install the box, they actually write the box into the racks, put the power supplies, put the line cards in, put the writing engine and so forth, power the box, boot up the box. Box was basically booted. So they went online and actually started to configure the box, TACACS, loopback, interface, IP address on the interfaces. Then they started to ping the interfaces around to see actually if the links were live and so on. And everything was clean. Therefore, let's put this box in IGP. So let's configure IGP, put high metric on it, make sure that this box is not yet in the best path. And adjacencies came up, everything is good. So let's configure BGP. BGP came up, everything is good. So the team did the dash checks, everything is fine, clean, yeah, can ping everything, clear the counters, look at the logs, no. Let's actually drop the metric into production metrics to become part of the network. And as soon as they do that, the NOC starts to receive black box monitoring alerts. And it checks, we don't know, it looks clean. And the NOC says, you know what? It happened exactly at the same time that you guys did that, so it's got to be you. So we can't see any problem. So they raised the metric higher and took the box out of the topology and started to troubleshoot. And they realized actually when they assembled the box, they forgot one kind of key element of the box. They forgot to put the switch in fabric. So the packet, the writing engine could actually talk to each other. The writing engine could talk to each of his neighbors because the path is not going through the switch in fabric. The ISIS will come up, BG will come up, everything was fine, except the box could not forward any packet. That was pretty bad. That was not a Google, of course. So that just showed us that, yeah, it's the locally generated packets don't actually go through the right path, so therefore it's not actually useful. So in order to actually to do exhaustive coverage, so first of all, with black box monitoring, when you send packets through the network, and they drop or you lose them, you basically wonder where they were lost. And you have to, the problem with black box monitoring, you have to go back in time and find the state of the network when the packet was lost. What was the best path between the endpoints forth and back when the packet was lost? It's a really, really hard problem to solve. And therefore, that's why we do troubleshooting. So instead of doing that, our solution was to use source-based routing. Because if you use source-based routing for all our test packets, we can actually tell the packets where to go and through what path. Therefore, we can say, I'm going to target every single node and link in the network because I know I can tell the packet where to go. And also, I will know where it was supposed to go if I lose it. So if I've got enough flows of source-routed packets like this, and I drop some of them, I've got a list of suspects, that suspect interfaces or suspect nodes that were on the path for sure. And if I actually take all those suspects together of all those flows and I intersect them, I may actually find the culprit. So it's a much better way to actually do our coverage. So yeah, and also it makes it possible to correlate. We can correlate things. So what we use actually MPLST. We use RSVP, non-CSPF, signaled LSPs with strict EROs. And that's basically how we've done our source routing. So, but more importantly, we don't want to test links only. We don't want to test simply links and nodes. We want to test the ability for a router to actually take a packet from any kind of ingress and be able to switch it to any kind of egress. So we want to test all combination. That's a lot of flows, but it's much more important than just links. And this is actually a core distribution access type of network. And just to give you a mental picture of what it would look like with all those tests, that's basically what it looks like. So it's a lot of tests. Also, actually, yes, these packets are processed in strict I and the highest quality of service. So if you drop something, you have to investigate because that means your search traffic was lost as well. So we don't want to let that. So, and now I'm going to hand over to Ross, who is going to actually talk about the correlation engine and the mapping engine. Ross.
Thank you. Thanks a lot. Yeah, Nicolas is from network engineering, and he came up with the whole concept, and I'm from the software part of network engineering, and we decided to work out how to implement this. And so the first thing to do was, okay, we've got these paths, how do we actually find the culprits? And that was a very interesting problem, and a lot of fun to solve, actually. So clearly, what's a correlator got to do? It's got to find the faulty links, firstly. It's got to have as little as possible false positives or false negatives, because our operations guys don't like to be annoyed with things they can't do anything with. If they're given an alert, they want to know where it is so they can fix it as soon as possible. Also, they want to know how bad the fault is. Is it 1 packet in 1,000, 1 packet in 2, or whatever? And also, we want to store it for the long term, so we can firstly see the trends and also go back to previous events and see what actually happened at that time. So we wanted to create a time series for every single element in our network. So we knew what a correlator needed to do. The tricky thing was, how hard or easy actually is it? So just to give you this is really just to give you an idea of what the problem looks like. Here's a very simple network. It's obviously a lot simpler than the network we're actually analysing, but it gives you an idea of what's going on. So here's a simple situation where the coloured paths are all the different. These are our LSPs, or our traffic engineered paths that we've created through the network, and we're sending packets through those. And basically, imagine if a fault occurs there, and this is a nice simple fault. There's a cable break, or something which causes 100% packet loss, and that actually, looking at that, it looks quite simple. As you can see, every single LSP going through, every single path of LSP, which I'll call them most of the time, has gone down. If you look at all the down paths and look at what they've got in common, if you do a simple set intersection, you can see that it's R3, R4, and clearly that's where the problem is. And if the world was like that, this would actually be a very simple problem to solve, and I wouldn't need to spend quite a lot of time working out the algorithms and writing the code for it. Yes. But it isn't simple, because firstly, our network is made of lots of. We've got bundles which certainly have multiple paths in them. They might have 4 different components, 8 different components in a single logical link. And as I'm sure you know, people who are familiar with traffic engineering, the paths are engineered at layer 3, not at layer 2. So one LSP could go through a component which is working, while another component could be broken. And also, you've got situations like you don't know the hash, and you really never know the hash. And then you've got situations where you might have very low packet loss. So you might have lots of LSPs through a single link that work, and one LSP that doesn't. So how I look at this, it wasn't a one-to-one and on-to type relationship. What I mean by that is, if you knew a path was bad, you knew that there had to be a bad component. But if a path was good, you could still have bad components, and that's the really important thing to think about. Because otherwise, the solution would be simple. You could take all the bad paths, look at the components of the bad paths, and say, okay, let's mark them possibly bad. Then look at all the good paths, say that they're definitely good, then subtract definitely good from possibly bad, and you have probably bad, or almost definitely bad. Nice, and we actually wrote a correlator to do that, and for simple situations like the one I showed you earlier, it worked beautifully. But in reality, you get situations where you can have multiple faults. Well, firstly, you get the situation like this, where you can have just packet loss on some of the links, and then you can have multiple faults. So you have a situation that you've got to work out which LSP is causing which bit of loss. And now, again, the situation of 2 is actually quite simple to do. When there's 7 or 8 or 9 or 10 or 15 different faults, and some of them are long term, it becomes actually a computationally difficult problem to do. So what we tried first, again, reasonably simple-minded, we said let's make an average. We've got lots of, if we have lots of paths through an individual link, then we can just average the loss. And typically where the loss is bad, you'll have a high value. Where there's no loss, you'll have a low value. Unfortunately, if you've got something going through 10 different links, and one of them has has a problem that loss gets shared amongst them all. So you tend to get hills rather than the error is, in position 1, position 2, and position 12. It said, oh, it's round about position 1, round about position 2. And I showed this to the network operations guys, and they said, well, that's beautiful. Beautiful graphs there, but can't do a thing with that. I don't care about how good the technology is. That's not good enough for me. But we did see that if you did it one pass and then took the high points and said, well, it's probably there, and effectively ran the algorithm again, we got better and better results. But again, we thought, we're mucking around with the edges here. This feels like an optimization problem. And this was our eureka moment. We said, okay, let's think about things being broken or working. And so we take all the paths, we classify them as good or bad. And how you define that is up to a second problem. Once you do that, if you can mark a problem as, if you can mark a path as bad, then you know that it has a bad path. That's the one thing you do know. And yes, so what you need to do is what you really need to do is find a list of bad components that covers every bad path. And clearly, that way you've got an answer for every reason. So you've come up with a set of paths, sorry, a set of links where one of those elements is in every bad path, and therefore you know that that's most likely the problem. And really, it just comes. So now this can be framed in a standard. So we frame this as a Boolean linear programming problem, using good old primal simplex and stuff like that. So traditional set cover problem, and this was literally our eureka moment. We did this, and we started to get very good results. So the tricky thing was getting the optimization problem. If people are familiar with linear programming, you need to set your constraints, and then you have your function which you need to optimize, either maximize or minimize. That's what we did. There was lots and lots of research in this about how to get this just right, but basically we worked out that if you try and minimize the number of links, and I'll have a glass of water, and make it as unambiguous as possible, and bias it away from solutions that are too simple. By that I mean we have sources of packets. Clearly, if you've got 3 sources of packets and you've got 4 errors, the easiest solution is to say, well, it's the 3 sources of packets which are the problem. Clearly, and usually that's not the case. So basically, by balancing A, B, and C there, we were able to come up with something that almost magically, once we actually put it into production, produced very good results. And it produced the Boolean results that operations guys need. This is broken, this is good. And then they could proceed very nicely from there. And of course, sorry about them. I made some horrible typos down there with the packets there. Basically, it's 98 packets over 100, which is 2% packet loss. I think my fingers just go crazy sometimes. But we did use the good paths. We used the good paths once you've worked out which ones are bad. Then suddenly, every good path, with every path, you can say, well, if it's bad, it's all in the place where it's bad. And therefore, if you've got, say, 10 good paths and one, or say 9 good paths and 1 bad path, you can average the packet loss because you know it's all related to that, and you can get very precise results. And that's especially what we get. We get situations where it says, we say, 1, you've got a fault, and 2, it looks like it's 0.01%. And we've actually gone correctly down to as low as 10 to the minus 5. So 10 to the minus 5 in our packet loss. So it's 0.001%. And we can reliably do that, which has been absolutely a revelation. And we never thought we could get that well. But that's how well it's worked. And this is how we did it. We did it, I imagined using the photographic paper of the old days, where basically, if you look at a star long enough, you collect the photons and you can actually see it. So if you take a path and it only fails, say, once every 15 minutes, if you take a 15-minute exposure, then if there's a path which goes like that and a path which crosses it but only fires also every 15 minutes but at random times, over 15 minutes you actually get an intersection and you can see. And so what you do is you're trading temporal accuracy for spatial accuracy, and it's just a typical trade-off, and that works very, very well. So when we run our correlation, we run it 15 seconds, 5 minutes, 1 hour, And there are different trade-offs between the two things. That works exceptionally well, and that's all in production and working very, very well. So basically, so what we did is, this is the black box versus white box, and I like to characterize it by saying that, with white box monitoring, you basically, know exactly you know that there's something coming from it, you know where it's coming from, but you don't know whether it's bad. You have a log message which says, FCS error 23, and you go, well, that's nice. Sure, it's coming from that box, but does it really mean I'm losing packets? And with black box monitoring, you know there's a problem, you lost a packet, but you don't know where. And so they've both got, and so we actually know there's a problem. Firstly, we know there is a problem, and two, we know where it is. So we've actually been able to get the best of both worlds by adding topology into the mix and some nice correlation software based on the linear programming. And it also means that when you've got simple devices, they mightn't have SNMP, they mightn't have sophisticated ways of doing white box monitoring. But as long as you know that your packets go through the element, they in the topology, and then you can find out what they are. So it scales very, very well to very large numbers of very dumb routing components, and without having to do SNMP monitoring, which gets out of control. Plus, every manufacturer has slightly different ways of interpreting the SNMP errors. Some don't even have SNMP. This basically judges the network by what it does, not what it says it does, and that's incredibly important. So quickly, the correlator couldn't work well without a good map, and a good map is something that covers all the components in a way such that there is as little correlation. Well, no, correlation is a bad word. So that every path is as different as possible. Because when you take the intersection of two paths, if they share 5 links, then you haven't got much information. If they share a single link, then you've got tons of information. But still so again, it's another sort of optimization problem where you need to cover things well, and you need to cover extensively or completely, and you also need to do it as a random. What we actually basically do is we're trying to maximize the entropy of the paths, and if we can minimize the amount of control plane we put into the system. Add to the system, I should say. So basically, we end up with quite a simple algorithm which basically enumerates the paths, beats a path to them, basically using SPF, but every time it uses a path, it increments the metrics and reruns, and so SPF gradually merges away from the shortest path, and you end up with effectively a nice entropic system of paths, which don't intersect too much, and again, make the correlator work. The correlator couldn't work without a good set of paths, so it's very much a symbiotic relationship between the two. And it worked well. We could keep things within limits. It didn't affect our production network, except in a good way that we found the faults, and it worked excellently. Pretty much from this point on, this is the mapper and the correlator. We wanted to automatically track the network as it changes, and also possibly, as the correlator can say, okay, it looks like we're losing packets here, but I haven't got much resolution. Could you create some new paths quickly to make things better? And that's what we're heading for now. But now on to Nicolas to finish up, because from the network engineering to talk about what we actually learned from this process.
So what did you learn? Yeah, so as was said, it works pretty well. We found problems that nobody knew about, things that basically were not monitored by black box monitoring, and we just assumed was working. Silent drops are not frequent, but they do actually occur, and it happens regularly. We found actually very low-level packet loss, and yeah, so low that people didn't trust us and say, you know what, it's pretty much, it's a fairly basic at the end. If it finds it, the packet don't disappear, the packet loss. So the most important thing we have, beside finding errors that actually occurs in the network, we also actually can test, and I mentioned that before, but it's really important. We can actually test links and devices before they're in prod, because we source route the test, and you bring a new node or bring a new link, you can say, I want to send, hundreds and hundreds of thousands of packets through every single link, every single path of this node before putting some real traffic on it, and suddenly you realize that maybe you have a hardware problem, maybe you actually have a DOA, it happens. We basically, with the amount of chipset that we have in this box these days, there's probably one chip basically being dead. And finding it is not fun. especially if we actually put search traffic or YouTube video for it. So it's really important that actually we manage to find, so we can actually find those mistakes before putting live traffic. Then the other thing we found was we took RSVP for granted. We basically discovered that our vendors take a liberal interpretation of what RSVP should do. We actually expected that if we tell RSVP to signal a certain path with a set of arrows, it would just do so. But because actually we tell which path to signal and then we tell that path, we actually know if they do, and sometimes they don't. And I guess it's a bug or a feature. Actually, in some cases, we thought it was probably a shortcut to provide better convergence, but breaking the protocol as a result. So that was interesting. So now we actually not only monitor the network, but we monitor also the RSVP signaling protocols. There's some limitations. It's not perfect. It's pretty good. We're happy with the system. It's not perfect. As Rod said, the pathing is not at layer 3. Therefore, we have to, when we have bundles or lags, and with large number of members, we need to have a large number of flows to make sure that we hash across all members. And we don't know the hashing algorithm of the vendors. They don't want to tell us. Therefore, we have to do a lot of guessing. It creates a lot of state. As I mentioned before, we don't want to test links. We want to test ingress to egress. If you have a lot of ports, that makes a lot of paths, that makes a lot of state at RSVP level. And it takes actually a fair amount of processing, depending on the size of the network. But creating, optimizing the map, and sending the probes for the edge, and collecting the result and correlating and reporting every 15 seconds, it's actually, it takes a fair amount of processing. So that's basically what we've done. There's one more thing that we're working on, and that's to reduce the state. We're thinking, how can I actually drop that state? How can I do all those paths? Tell the packets where to go without using RSVP. So we tried everything. We tried IPv4 source routing. It didn't work very well. I mean, the vendors these days don't support it. It's IPv6 source routing. It's been actually had mid-draft, and there's no viable solution. So we actually found a way. So we thought actually, let's say if you want to send a packet through, A, B, C, D, and back to BA, nice loop. Routing protocols don't like loops, and it's not always easy to achieve. What we actually came up as an option is to do a one-hop static LSP. And we map actually each interface with a label. And obviously, I will use like interface 1 as label 1. Obviously, it's not label 1, but just for the illustration, we use label 1. So basically, for each interface, we'll actually associate a label with a one-hop static LSP that basically says, label 1, send to interface 1, and pop. So then we have this loop. We want to send a packet through that, basically A, B, C, D, B, A, for those ports specifically. So what we do is simply stack a set of labels in the packet. So we put the signaling not in the RSVP signal, but actually in each packet. And so when the router A basically finds a packet with label 1, it just looks up the label, sends the packet through interface 1, and pop. And then actually, if you do that at each hop, basically router B receives the packet, and this time the top of the label stack is 2. And it basically looks up label 2, send the packet through interface 2, and pop. Router C receives the packet, again, label 2, looks up the label, send to interface 2, and pop. And all the way back to basically router A, bottom of stack, send the IP packets. So with this, we could actually send packets for an arbitrary path in a network, doing source routing technically, and having no RSVP state. So we could actually do 1 million paths without actually having next hop. So the only next hop we have is actually the number of interfaces we have in a router. So that's the end of our talk, and that's basically what we do. Again, the message is actually source route your packets. If you want to test your network, if you use destination base, you're going to use your routing protocol, and your packets are going to avoid the failures, or they're going to actually, the state of the network will change very rapidly. It's really hard to find where the packet went.
I think we have time for a few questions, if there are any. Go ahead.
Yes. We do have a remote question from Matt Fitak, okay. And he asks, how many paths did they have to build for this mapping? So I think he wants to know how many total paths you had to build.
So how many total paths? It depends, actually. It basically per link. So we have some we have some constraints on basically router. We don't want to exceed. We actually monitor the transit path on each router, so we try to keep that to a certain level. Actually, we took a line in the sand instead of fathom. It should not actually exceed a fathom paths on each router. And then actually the amount of path is probably detected with the amount of member that we have per bundle. So we tried actually to cover each member and make sure that we hash. And we had some heuristic there. We said, okay, we need 4 times the amount of flows that we have of members. So then you multiply that, and depending on the size of the network, you get a different number of paths. But yeah, it gets large, obviously, in large network.
I mean, you can say about, say, 10, as a rough rule of thumb, we had about 10 times the number of links in the network. And that's assuming the links are actually bundles as well. Yeah. Okay? So that's a rough rule of thumb there.
Yeah.
Are there any other questions? One last comment, and the code for this will be available, open source?
It's not open source yet, but
Honest attempt.
Yes, ping us if you have any questions. Those are our email address, and we're happy to talk about it. If you have actually another solution for the same problem, we'd love to hear about it.
But yeah, if you can source route packets, collect the results, and then get your friendly neighborhood linear programming system to solve the problem. And I'm using GLPK, which is the GNU linear programming package. So I didn't do that. I just reduced the solution, sent it to it, and it comes back with the answer, which is very nice.
So there is a monitoring trail, the topic, in the research community. I don't know if you heard about it. It has similar idea, using multiple parses to cover the link failure and then infer what link was failing.
Okay.
It was using similar approach like you guys were doing.
Well, I think it's a good idea.
Monitoring trails.
Good. All right. Thank you.
Thank you very much.